Bismillahirrahmanirrahim. In this video, we will learn how to use the Autodesk Fusion to create 3D model, solid model, and do simulation, buckling analysis, and also nonlinear analysis. This is the interface of what we call it Autodesk Fusion. So you can find on top here the quick access, normal, undo, redo, and then also file here. You can open and save. And then this one, data panel here. Any model that you already created will be listed here. Just simply close it. And then on top here, under the main menu, or you have the what you call it, your login, and then help. And then if you want to create another design, you can press this as well, or you can create a new design here, Control N. Okay, currently it is untitled. I haven't saved the model. And then under the menu bar here, we have several tabs here: solid, surface, mesh, sheet metal, plastic, and utilities. So in this video we will cover the solid, and then modify the solid and ensemble the solid. Ensemble the solid, that the bodies that we converted later to component, and we assemble it. So in Autodesk Fusion, it has several capabilities for design, generative design, render, animation, simulation, manufacture, and drawing here. So simulation, in this video will cover the design and simulation. Okay, and then down here we have free orbit. So basically you can also move around or rotate the model using this. On the right side here, there is the cube, and then but also you can have this one, free orbit. When you click this one, there is a circle orbit that you can move. And then here look at, this one is panning, or zoom in, zoom out, or zoom window. Display setting here, you can change the what you call it, change the environment. Visual style here currently is shaded, shaded with hidden edge, and then wireframe. So some visual style important to access the object behind. Environment, we have this one currently infinity pool, effect, internal dome, ground plane. You can explore it on, and the grid, and this is viewport. And then at the bottom here we have this one will be what you call it, step of every single step that we are doing when we construct a model. So it will be placed here. So then, other than doing the undo, so you can directly jump to the specific process. And then on the right corner down here, you have the option capture the design history or hide all. You can select that one. Now on the right side here, there is a what you call it, quick setup. So you can release, you can expand it. Then there is a quick setup here. We have setup the default unit in millimeter. For the detail one, the detail and small object, better use millimeter, because we deal with the, let's say, the thickness, better we use the millimeter. And then CAD experience. So there are several experience that you can refer to: Inventor, SolidWorks. Maybe you are more familiar with SolidWorks and Alias, so it will give you almost similar or familiar control. And then this one for to pan, you can see here we have F2 plus right click panning, zoom F3 plus this one, but normally I press the shift button and then using the right click, but you can also have later on by click on the right side. Here we have to move, press, pull, hide, sketch, and so on and so forth. Okay. Currently we don't have any model yet, so we will start to create a solid model by sketching the profile, its profile. So here, so we start create the profile, click this one, and you can see there we can start from this three plane. You can start from here, you can start from here, or you want to start from here. I will show you on how to create plate girder. So later, okay, plate girder, the eye section, profile, and then we add the what we call it, stiffener. So then maybe better this one, so then we can extrude along this one, along the so then the axis will be y axis, z axis, yz plane, and then the x is the extrusion length. Okay, let me start from here. Okay, then to start to construct, so you can use the line here, or you can using this one, because we have the modify fillet, chamfer, blend curve, offset, so then we can utilize that. So this is almost the same of doing the CAD. Can start with line. So as I mentioned so the way we construct a model will be different one to other one. I mean everybody have the way to construct. Maybe start with line, or maybe rectangle, or after that do modification, trimming, offsetting, and so on and so forth. So then this is my way. So okay, let's say we create what we call it, a plate girder, as in the design example. Okay, here the line, so it has a depth of what we call it, 2000. So I will write 1000, and then I will what call it, mirror it better. So then I have 1 meter here. Then after that, so you can move here the what call it, the dimension. So you can add the dimension here, sketch dimension. Okay, see under the create here you can have the line, rectangle. Rectangle we have the 3 center rectangle or 2-point rectangle. So sometimes this one is easier, but up to you which one that you prefer to start. Okay, and we have also mirror, and then a rectangular pattern, projection, and then sketch dimension. Okay, then after that I want to offset the thickness of the what you call it, of the plate girder is 15 millimeter. So that we do offset here, and then offset you can offset to the side, one side or 2 side, right? And then here, and then you can see there, you can stretch by increase the dimension by stretch this one, or you can write over there 7.5 millimeter. So this is the thickness. Okay, then after that we create the flange. Okay, the flange, the thickness of the flange is 20 millimeter, and then the width of the flange is 750 millimeter, something like that. So then what you can do here, you can create here, or maybe you can create this one using this one. Wait, thickness, you can see here the currently active dimension, horizontal, sorry, vertical one 75 millimeter. So then you can type here thickness 20 mm. Oh, sorry, the active one is the horizontal. So then you can write it is 375. Okay, and then to to panning that one, my drawing, I mean my sketch, I press the roller of the mouse like that. So 375. Then after that, the thickness, you can press tab, so it will active to the vertical line. Vertical dimension is 20. And then enter. Like that. So then, so you can move this one to the other side here. Then after that, you can see here, we can do mirror basically. So you can delete this one, trim. So using this one, this trim, cut scissors here, so trim. Okay, so then after that, we select escape, and then after that I select this one, and then I do mirroring. Mirror, and it will ask you mirror line. So use this one as the mirror line. Select, press the select one, and select. As you can see that the preview mirror lines or profile. So then after that, press OK. Escape. Then after that, you do modification. Trim here, trim here. Another one, trim the line here already, and then done. So you don't need this dimension maybe, so you can delete the dimension, because later we will delete here, the middle here, and delete. Oh, sorry. Delete like that. So you can trim this one as well. Okay, it's warning because no constraint anymore, but it's okay, no problem. Then after that, we do mirror one more time here. Create one line, because mirror we need to have a reference line for mirroring. So escape to to end the command. Then after that, we just simply select. You can select from left to right, or from right to left. So from right to left, any object that intersect with the rectangle selection will be selected. Then after that, do mirror here, and it will ask you where the selected where the mirror line. So this is my mirror line. Click here, then done. So I have the profile. Oops, sorry, I press unintentionally. I press the escape button. So I select from left to right, from right to left, sorry, from right to left, and then press mirror. It asking me the mirror line. I select this one, and after that I press OK. So it's mirrored. Then after that, we delete this line. Done. Okay. So if you want to have line, sketch line here, from top here to bottom here, I mean So you got the 2000. Or you can place a experiment here or here is no problem. 2000. So then you can also do editing. So to 2000. So you can adjust, still can adjust. Let me try to adjust this one. Make it 2100. Oops, it's not locked. It's not locked. Sorry, the line here locked. Sorry. So it's supposed to be. Oh, no wonder, because this one you can see here it is not closed. So we have to close it first. So then it will become a constraint to make it one surface. So then you can escape here and then change the 2100. Oh, still not. Okay, anyway. So you have to maybe this one. But anyway, it is not necessarily you have fix and fix here. Anyway, you can manage to have it done. Let me see what is the fix and fix here. Lock the size and location of the point or object. Okay, so basically we have that one. So then the eyes profile already created, and then later you could explore the constraint here. Tangent equal horizontal vertical. Okay, here actually basically it will lock the, it's become a constraint of the model. Then finish sketch. So you have this profile. Then we continue with this one, extrusion. Extrusion for let's say we will extrude it to 3000. Okay. And then I press the shift button and then press and hold the scroller of the mouse, and you have this one, and then you can do 3000, let's say. Done. 3000. So then we can add stiffener. And so you can see that we have. So there are two ways to create stiffener. You can create another component, and after that you combine it. But for this time, I'll show you on how to create the stiffener from the body that we already created here. Okay, so then you can create this one, create sketch, and then select the surface, this surface. Then after that you just simply create the stiffener using this the point there, and then you can see that the thickness is 15 millimeter. And then after that anyway you can, it's not you can edit later on here. If you want to check design, create sketch dimension from this line to this line, 15. So then you can change, or you can edit. Let's say Ctrl Z. Let's say so then you can see here you can move down here. I can drag to the previous one before the, or you can create this sketch here, or you can select the unsave this one, so before the sketch. Anyway, so here let's say we can still drag this one. Oh, because we already have a constraint here. Let me release the constraint here, delete, and then you can still adjust. That's all. Then if you want to set the dimension, you create here. Create sketch dimension. You select the edge here, and then the edge here, and then set 15. Like that. Done. So we escape, finish sketch, and then we have two surface here. So basically we can split the surface by this line by the existence of the lines, or we can also split the surface by using modify. Here there is a split face. Anyway, so then after that we extrude a bit, we rotate, and then select this one. So how much we want to extrude, let's say 100 millimeter, and enter. So then the first stiffener created already. Then I want to construct my stiffener also here. So create, press this one, the surface here, and then after that same, select from the end here, and we can create, not necessarily directly to set to 15 because it's quite long. Then after that you create the sketch dimension, this point, and you can set this 50. Okay. Then finish sketch. Then after that we extrude. You can create the solid by extrusion, revolve, swap, loft, whip. So then later we explore this one. So select the surface, and then how much you want to, this one 150 or 100, enter. Okay, done. Then the other side here, back face, so same goes here. We select this one and then click surface, the rectangular, and then after that click the sketch dimension 50, done, and finish sketch. And extrude. How much you want to extrude? Say 100. Yeah. Then here we add another one here. Create this surface. Okay. Rectangle. And then so you can see the sketch here. You can see here. If you want to have the previous one, so you can switch on, so you can see the sketch available at the back. Previously you cannot access it, you cannot see it. So by switch on this one, you can see at the back. Or you can do look at. If I'm mistaken, we have this one, or maybe look at here or not. So there is a what you call it. You can see the profile behind. Okay, then create the sketch dimension. Click here, and then 15. Done. And then we end finish the sketch, and after that rotate a little bit, and then extrude. Let me see, check the, okay, correct, sorry, extrude. It is because I switch on this one. So here, extrude. So we type 100. Done. So then you can see here is a one body of the girder. then it is ready for buckling analysis or non-linear analysis. But the limitation of this one, so you cannot control the stiffener materials. I mean, if you want to have different materials for the stiffener, so you cannot do like this. You have to create separated component and then you assemble. Yeah. Okay, so let me have this one, and then we move to simulation. So it will be bring to simulation, and then you can see here a new study that we can conduct: static stress, model frequency, electronic cooling, thermal stress, structural buckling, nonlinear static stress. So then for this video, we will conduct this structural buckling and non-linear static, or maybe you can also go for this static stress. This one, these three. Okay, these three study. So we start one by one. Create study. Start with static stress. Create study. So then we have here study static stress. At the corner, at the end here, I mean this icon, you can right click and then set the setting. So you can still select static stress or structural buckling or linear static stress. You can select from here, and then the mesh, you can change this scale mesh. You can adjust here for the meshing, or if you want to have the adaptive mesh refinement, also here. Say especially on the corner one or on the curve one, so then it's more denser, so it is not look nice. Maybe we can change the visual style here to set it with hidden edge, like that. So we can see the edge, like, okay. Or maybe you can see the visual style visible edge only, like. Okay, then material, you can change here. Currently material is not set. You can select by pressing this one. You can select this one from this, so then it will be listed, but most of the what you call it, material here is not, it is linear, not non-linear. You have to set the advanced properties, then it will become linear. Let's say, but for the static stress analysis, so we can use any object here, I mean any material here. Let me select steel, steel here. So if you want to see the properties of the steel, this is the steel properties that we can use. I mean embedded to this one: density, the Young modulus, Poisson ratio 0.3, yield strength 207, quite low, ultimate tensile strength 345. But anyway, you can go for the and select other materials if you want to have the higher strength. I can see you can have this here, height, strength, structural, or you can select based on the the material here, mild steel, and other things. And then remember that this is one single body, so you cannot assign different material to this body. Okay, then just cancel this one. Sorry, material. Sorry, you can select this. Check CMS body. We select the steel. And then press OK. Okay. So then down here we have steel for the whole body. And load cases. We have the load and the constraint. So this is the step for first applying the materials. So you can access elsewhere from here: material, study material, material properties, manage physical materials. If you want to use other material from the library and then modify it, you can use this one. And then constraint, structural constraint. So for the purpose of stress analysis here, let we set this one as what we call it, cantilever, and then fix for the whole area. Or if you can do as well like this. Let's say the Z1 not fixed, so then you can set this surface, select, and then this surface. So it is fixed for UX and UI. UZ is not fixed. And then you can fix the Z on this one. So sometimes if there is a warning or problem of less of issue on the what call it singular matrix or something like that, so it is sometimes it is because of the insufficient what we call it constraint. So let me start. So then I just want to give you some example here. So you can set a constraint here. Let's say only for Z here on this surface. The surface. So it is not moving about Z axis about that one. And then you can place this one, or you can just simply set it fixed at this point. Do I press the button? Let me cancel this one because I unintentionally press one. So then use it, select this surface, make sure it is highlighted. That one. So I want to see the stress of the linear stress without having torsion happen on the girder. Then press OK. So we have this one, and after that constraint, and then the load. So gravity, we untick this one. So if you want to add another load here, structural load. Structural load, we have force, pressure, moment, bearing load, remote phase. So then you can explore it on. So we select the force here, select the surface, we select this surface. Then we select the direction here, we select the vectors. Vector here, vectors. So then about y, negative, say 3000 Newton is too small, 3 million Newton, so 3000 kilometer. Yes, okay. So 3000 kilometer. So based on our calculation in this example, design example, so the buckling, the buckling strength of the buckling capacity, buckling design resistance of the girder, and about this size is about 2300 something, or 2700 something, I forgot. You can check in the design example that I sent to you. So basically we almost done, and since it is only a single body, so we need to have this contact. So you can have the automatic contact, it will detect if you have different many component assembled together. And then mesh here, so you can right click and then generate the mesh. So it will generate the mesh, but I think we cannot manage to have this tetrahedral. So if you want to edit the mesh setting here, and then maybe you can change scale mesh size per part, so then it will check. It's not regular, so it will detect the depth, the thickness, the size here, so then it will be more denser. And then let me okay, I take the scale mesh size per part, okay, and then after that regenerate the mesh. So actually we can directly go for detail, for the simulation, because during the simulation it will check the mesh, and then if the mesh is still not available, it will click the mesh. Okay, so then the mesh already done here, and then this one pre-check. So anything what you call it, it will give you prompt here if anything is not suitable. Okay, then you can solve, press this button to solve, and then automatically the solve it is, because we in the account the education, you can see what you want to see. You can show the solve studies with error, cloud credit, and cost balance. So you can see here the cloud credits only 0 for the stress analysis, but for the education we have the unlimited one, unlimited available, unlimited. Then solve one study, press this button. You can name it, let's say we name it as Girder, and then save. You can create folder. Previously it is under CASP333. Okay, then this one, you can see it is running, and I need to wait a bit. You can close. So currently we run the static stress. After it is finished, we create the buckling, and then the nonlinear analysis. But we job status currently is 7% already. It's supposed to be faster compared to analysis, because it is a linear analysis, linear stress analysis. And it also depend on the numbers of what we call it, mesh that you have. So the denser the mesh that you have, the longer it will be the analysis or the simulation process. So you can see it's already 95%, then almost done. You can see that actual minimum safety factor 0.58. So then you've got the safety factor, deformation scale adjusted, from you the result status, and close. So because it will from you, because the applied load may cause your design to deform permanently. Yeah, because this is our intention to have very excessive load applied. And then you can go for a different stress here. This is the fundamental stress, and you can see here. You can see since the load is also applied on the flanks, so the flanks also deform. But you can change, adjust, or actual one is very small, but it will deform. So there is an prompt you that there's a prompt here mentioned that the load is very high, so it will deform permanently our model. So it will not give us any buckling problems, because it is linear stress analysis. Then we have no any step here. So then we can see the displacement, strain, contact force, and stress here one misses, or if you want to see the first principle, third principle, or XY plane. So XY plane here. See XY plane. So you can have some more information here. And then you can also use the inspection here. surface probe, create point probe. So it is more very important when we have the nonlinear study. So you can see that particular area when it start to yield and deform permanently. Okay, that's so you can remove the maximum and minimum stress here by inspect here, height, minimum, maximum. The display, control the display for the load. Inspect. You can also explore later on by yourself. Okay, done here. So let me duplicate this one, clone the study. So we have study number 2, and then change to buckling. You put and then setting here. We select buckling, structural buckling, and then how many numbers of model of buckling mode, and then press OK. And then here for buckling, the load we need to change to 1000. I mean, this sufficient if we have this 1000 MD, 1000, because the eigenvalue times the applied load will become the buckling force. Thousand Newton. Then press OK. So then please check here. Does anything I have no need to change. Or if you want to change you can change the instead of I mean the constraint here not fixed about Z, so maybe you can set it to fix and remove all these 3. Can also like that. But anyway, we continue with this one. Then we just go for this one. Then you can see here cloud. The cloud credit 6, but we have the unlimited one for education. So study. So it is a good thing for Autodesk product. We as academician and student can utilize full features of their product, selected products. Simulation model 1. Name of the main the model simulation level 1. So it's quite fast, 5%, 7% over. When it is failed, it will inform you as well. But normally stress analysis and buckling analysis, the support condition play a big role, and then the rest will not. I mean the other. If you run the nonlinear analysis, so you need to make sure the material is nonlinear, have the nonlinearity, nonlinear materials, and then for the support condition, degree of freedom, you need to very careful, very particular that one. And then nonlinear analysis also the splitting of the convergence value or bisection, call it bisection. So it is good, a good step. You run the linear analysis before you run the what you call it non-linear analysis, especially for the plated structure. You run both linear and buckling. So the buckling will give you the what you call it the buckling strength. I mean the buckling load. So then you can assign the load for the nonlinearity based on the buckling load. So you can see here it's already done, and then you can close here. You can see the buckling shape appear here. If you want to display the what you call it the mesh, you can press this button, and then you can see here there are 3 modes here, and then you can see the range of the buckling eigenvalue. I mean, this one you can see here, buckling times load. So it is become the buckling load, the buckling load. Because this one is 3621.817 is the eigenvalues. Multiply with the load, give you the buckling load. Okay, so it's about 3600 kilometer. Then mode 2, so we can remove this one, and then let we remove the maximum hide the maximum and minimum. Let's see. So it's typical buckling. Save. And then the mode 3 is okay. So we have this one. So then for the if you want to do the non-linear analysis, use one of the buckling mode 1, so sufficient because it's the smallest one. Because if you place too high value, so it will generate an error because it is the deformation, the large deformation will occur, so then it will not be cannot be captured by the software, because there is a limitation on this one. If you want to use the large deformation mode, so you need to use different software. In this case, Nastran, Inventor Nastran. But here the buckling also happened to this. It's because of this one to 10. Maybe I forgot. If I'm mistaken, it's supposed to be 50. So the buckling transfer as well to the flange. If I'm mistaken, it is supposed to be 50 by 800, because this one is 220 millimeter to 10 for the flange. Okay. So then we have this one. Anyway, then we can go for non-linear analysis. Click this one, do set up the setting, and then change to non-linear stress, and press OK. Before we have to check this one one more time. In non-linear static, this one number of steps here. So the number of steps is also controlling the bisection. So let's say if one loading is not converged, it will do bisection. So it's reduce the load into half, something like that. So then this you can increase to 100 or to 200 maximum. By the design the developer they said that can increase to 200 and okay. And then the load here, load cases here, you can change to the load here. You can change the value to 3,300 Newton. So negative. Download. Okay. And then the material we need to change to non-linear material. Go here and then select the materials that, or you can press this button. Properties here, Fusion library. Go to here and then check whether you have surrounding structural. If I'm mistaken, it is. So then you can go to advanced material properties here. You cannot reach the Fusion server. Our service equality can not connected to the internet. Anyway, I'm connected. Okay, then we have here material browser. So can bring it. This is the favorite one. You can change here material here, and then you can press edit here. You can check appearance, if you want to change the appearance, the physical, the advanced properties here. The mechanical portion ratio, you can still you can duplicate and change the properties. The strength, this yield will be 248 is sufficient enough, because the buckling based on the value, the result of design example that we have, it will yield about 160 megapascal below the yield strength. So then let me see the advanced properties here. You can see here, this is the plastic parameter, this hardening rule, isotropic, yield criterion, warnesses, then initial yield stress. So already start this one, you can edit accordingly, and then press this button, you can see the graph. You can see here, this one linear, 100 something, so already start the yield, and then this is a long plastic hardening. Then okay, so press OK. So we use this one. So we use standard structural steel, and then gravity force, then we push this one. Oops, sorry. We have this linear study, gravity, contact, no magnetic contact now. Result, and then there is possible yield on the flanks as well. Once we select what call it, flanks, it's supposed to be 50. Okay, let me run here, and then the running time will be longer. Hopefully it's have no any error. So if it inform you that there's an error, there's two way to solve this one. Reduce a little bit the load and increase the the steps. Solve study. Okay, so start to simulate. Finally, we finished the nonlinear static stress analysis using Autodesk Fusion. So I have to do some modification. Actually, from the beginning, in the study static stress analysis, the result, so that when we activate this one, so the applied load may cause design deform permanently. Then the load that we use here is 3000 kilonewton. So it is already, it will give permanently deform. So this is one indication if you want to go further for nonlinear analysis. And then even in the buckling analysis, we have the buckling mode in 3600 kilonewton, but it is overestimate, and then it is because of the thickness of the flanks is not adequate. It is too thin, so then the deformation transfer as well to the flanks. So that's why we got the very high numbers of buckling load here. For the nonlinear analysis, is supposed to set up the load. In this case is 2900. Previously I tried for 3300. It failed. Because of large deformation happened. So then it's beyond the non-linearities of the materials, so it failed. And then we cannot set up the large deformation setting in Autodesk Fusion here. So then gradually I reduce. I have to reduce the what you call it, the load that apply to the structure. So, and then drastically at the beginning I start from 2600, and it is not reach the yield, and then it is still linear. So then we have to increase gradually until it is give us the yield, and then buckling form can be shown here. You can see here, but still because of the flanks too thin, so the flanks deform as well here. You can see here on the displacement it happened, and the graph here you can see at the step of, so here on 800 something displacement, on the step of 180. If you want to see the stress here, can you see that it already what you call it, yield. Oops, sorry. Result here for misses, you can see it is already yield at 186. So it is expected lah, same, almost the same value in what we call it, by design. By using buckling of plated structure. The value is 0.6. The C, which is the reduction factor for buckling. Is here buckling, is 0.6 times 275. That was the difference because of the material, different material strengths, and also for sure in the design code, the safety factor is also already embedded there. So that's why it's slightly different. If we multiply 0.6 times 275, 0.6 times 275, so it is 165 is the buckling. The yield reached when the buckling is occurred. So here is 156. So basically, the design is quite underestimating. So it's supposed to be can reach more. Can have more strength. But anyway, it is because of the different materials. So also the non-linearity graph is we use the standard one. Is not coming from the tensile test result. Okay, and then also here the result here we can add another plot here. If you can, as you can see here, we have stress formulas and also the if you want to have the displacement maximum like that. And then if we lock this one, it will follow when the the buckling start. Like that. Then move this one accordingly. You can see buckling is the sudden death. It's directly boom. Oh, it's not same. Oh, it's because of the stress. Let's see the displacement here. Buckling is the sudden death. You can see that. Boom, directly. When it's reached the yield, it's no sign of deformation. Suddenly fall like that. So that's why very particular Eurocode and the ISC is very particular on buckling problem here. So, okay, that's all. You can explore this one. You could also another one here. You can do comparison here. Compare, and then this one is compare the result here. If you want to see here, you can give displacement here, and then here, click here. Then you can remove the browser here, or hide the browser. and then select the displacement, I mean the stress, strain and stress. Normally we use the stress and then the displacement sufficient to determine when the yield is reached. Then finish compare to end this one. And also this one, deformation, you can set whether you want to actual deformation. Then you can see this deform 26 millimeter, but total displacement buat Z is 25. We can create result under this command result tools, whether we want to animate legend option and then report here. So let's say we go to nonlinear static stress. Both cases we can result step for show all or custom. So then review report. So it is in the HTML file, and then the loads and the result for stress at the step 200, all the only at the step 200, and then you make width, you can make it bigger or smaller, and then you can print it 50 like that. Okay, that's all. Thank you for watching.